We can only hope that that was not a graduate of Physics 24. And now we need to arm you as crane operators so that you will not suffer such an ignominious fate. Okay, so we would like to evaluate. So I'm going to simplify the problem a little bit. Go down. Is that better? Oh, really low. Good. All right, so here's the situation. We're going to have to evaluate whether this crane is going to take a drink. So what must be true if this crane is not to tip over? So he says the net torque on the crane has to be 0. Well, okay, so one of the tricky things about torque is that it involves not only the forces, but, yeah, an axis. So what axis do we have to pick? What's that? The front wheel? Excuse me. So this one? Right there? Okay. Is that a no? Is that the only choice?
The back of the place where the beam is attached to the crane.
Up here? Place where the boom is attached to the top of the admittedly goofy looking crane? Center of the beam. Does it matter? Does it have to be 0 no matter what we pick? For what would happen if it weren't 0? Then, yeah, bad things. Then it's going to rotate one way or the other. Okay? So we would need that the net torque with respect to any point is 0, and we would need that the net force on the crane is also 0, or it's going down. Okay. So here are the rules and the guidelines for solving statics problems. And I'll give you a chance to note those down while I try to reproduce the drawing. Yeah, we're proliferating. Yeah. That?
Then any force that's below that is not going to cause a torque, right? If that's our axis.
So he's saying, suppose that we pick right there as our axis. Then does the load cause a torque? No.
And so then there is a torque to the right because of the mass of the crane. Well, I guess there's the double force that balances it, so then there's no net torque. But then doesn't that seem to imply that the mass of the load doesn't matter because...
So he's, okay, so just if I can summarize, since by choosing this point as the point about which we compute torques, well, how about maybe what we should do is draw in the forces so we can just see what are all the forces that we're dealing with and where the torques might come from. So there will definitely be a gravitational force to the tune of m sub L g here.
But there's a force.
Okay, now, I think I gave a mass to the boom, didn't I?
Yeah.
Okay, so where does that apply? Okay, so at the center, and this thing was L? I don't know. I have to look back. Let's look back. Sweet, okay. So that is going to get applied at the center, which, okay, and, oh, D is the distance between the wheels, right? So D. Okay, so, okay, we have the boom, weight of the boom, we have the weight of the load, weight of the crane. Where's that applied? Center of mass of the crane. So my crane is of particularly simple construction. It's uniform density, whatever. Okay, normal force from the wheels. Okay, so I'm going to have one normal force, and I want to check to make sure I get the right N1. Okay. And another over here, N2. Okay, is that it, or are there other forces that I need to put on this?
Isn't there a force at the end of the boom that goes?
Isn't there a force on the end of the boom that go? So I guess I need to worry about what's my system, right? Yeah, so what should be my system? What do you want to pick as the system in order to determine if the crane is going to tip? Everything in the picture except the ground. Okay, so if this and that and that and then this are all part of the system, then the external forces would be maybe what we've shown, and internal forces. So, of course, this is a cable that's being used to raise that load. So if I took this mass out of the system, then and the boom stayed in, then I would just know over here there's some tension force from that cable. But I'm going to keep it as an internal force. The external force that's applied happens down here. Okay? So are you beginning to see why we wanted you to put the forces where they're actually applied? Because now it's really going to matter for computing the torques.